we're going to talk about sections 1.5 from the textbook and 3.5 from the textbook. So I know we're getting a little ahead of ourselves there, but there's a lot of stuff to do with limits at infinity and infinite limits, which is sections 1.14 and 1.15 from AP. So we've done some of these before, and it's vertical asymptotes, but we're also going to do properties of infinite limits, which is horizontal asymptotes sometimes. Our homework is over here on page 88. So first off, a limit in which f of x increases or decreases without bound as x approaches c is called an infinite limit. Okay, so that's when you say like a limit goes to positive or negative infinity. Those limits do not exist, right? Because there is no like cap on the y value. We just say that the limit equals infinity to be more accurate in describing how the limit doesn't exist. That's because a limit is supposed to equal a constant number. Okay. These kinds of limits happen when the denominator equals 0. Okay, but the numerator does not equal 0. Okay, so it's going to be like a number over 0. So where are we going to have some vertical asymptotes? Let's take a look at this first f of x from example A. We've got f of x equals 1 over 2 times the quantity of x minus 1. So we just say that 2 times x minus 1 equals 0. We set each factor equal to 0, so 2 equals 0, x minus 1 equals 0. 2 cannot equal 0. However, at x equals 1, x minus 1 would equal 0. Okay, so there is some kind of a vertical asymptote at x equals 1. Let's look at limits. The limit as x approaches 1 from the right of 1 over 2 times x minus 1. So if we plug in numbers that are just very, very slightly bigger than 1, what happens to this fraction? Does it get really, really high up positive or really, really low down negative? So let's just plug in 1.1 for x. So notice I'm not putting an equals sign here. Okay, let's do 1 over 2 times 1.1 minus 1. That is going to equal 1 over 2 times 0.1. So that's going to be 1 over 0.2. Okay, so that is going to be 1 divided by a very, very, very tiny thing. So that's going to be a very high up positive number. So your limit is going to equal positive infinity because this fraction was positive when you plugged in 1.1, which was slightly larger than 1. Let's take a look from the other side. So let's do the limit as x approaches 1 from the left of 1 over 2 times x minus 1. And let's see what that one is going to equal. So we're going to plug in a number that is slightly smaller than 1, which means like to the left. So 1 over 2 times, let's see, what's a number that's slightly smaller than 1? How about 0.9? So 0.9 minus 1. So that's going to be 1 over 2 times negative 0.1. And that'll be 1 over negative 0.2. So that reduces to a negative number. Since it is negative, that means that our limit is going to be negative infinity. Now, is that always going to be the case where the left side moves down towards negative infinity and the right side moves up towards positive infinity? The answer to that is no. You've seen limits where both of them go up. So that would be a case where both of them go up towards positive infinity. That happens when you get something like x minus 1 squared in a denominator. All right, let's take a look at B. We've got 2 over the sine of x. So we set that denominator equal to 0. So where does sine x equal 0? Okay, we know that sine x equals 0 at x equals 0. So there's going to be a discontinuity at x equals 0. Where else? 1 pi, 2 pi, and so on. At any of those, the denominator would equal 0, but the numerator would not. So that means there are vertical asymptotes. That's what kind of discontinuity it is. Third thing, alrighty. Let's factor the top and the bottom to see what those look like. Denominator is x plus 2, x minus 2. And most of the time when you are dealing with fractions and you're factoring, teacher's going to give you something that will cancel. So there's probably an x minus 2 or an x plus 2, which means the other one has a 4. Based on our signs, we're going to have a plus 4 and a minus 2. All right, so we've got a couple discontinuities. At x equals negative 2, that first x plus 2 would equal 0. And at x equals positive 2, the second one would equal 0. Now, we have removable discontinuities and non-removable. Removable discontinuities are things like wholes. We were able to remove that factor, and the factor is the one that makes x equal 2, the discontinuity. This one is not removable, so it is a vertical asymptote. So there's a vertical asymptote when x equals negative 2, and a hole at x equals 2. That's really it. If you want to take limits, you totally can. Just plug in a number that is slightly to the left of negative 2. You can plug it straight into this guy even, into f of x equals x plus 4 over x plus 2 when you take that limit. So you don't actually have to do it into the whole thing because we know that that second factor is going to be the same and it would just cancel. So it's like a reducible fraction. Alrighty, properties of infinite limits. So infinite limits, remember, are the ones where x is approaching a number and then f of x, the y value, approaches infinity. So for f of x, we're going to approach infinity, but for g of x, we're going to approach a limit L. So L is going to be a constant number. So the limit does exist for g of x, but it does not exist for f of x. Okay, but notice that x is approaching the same number on both of these guys. Otherwise, you cannot bring them together. All right, a sum or difference. Okay, if we are trying to add a limit that's like infinity plus L, that's like infinity and beyond. What's beyond infinity? Nothing. It's just infinity. So you cannot actually like bring those together. It's not like technically allowed. F of x times g of x, infinity times anything is still just going to be infinity. If L is less than 0, that means that L is a negative number. So if you multiply a negative number times a positive infinity, you would end up with negative infinity. Next, infinity divided by anything, like any actual number, is still just infinity. But a number divided by infinity is going to be 0 for the limit. If you have a normal number that is just a number, like L, let's say it's a 5 or something, and you divide it by something that is super, super gigantic, you're going to end up with a limit of 0. Limits at infinity are different than limits of infinity. Limits at infinity means that x is getting bigger and bigger and bigger forever. So you're going like super far to the right on the x-axis or super far left on the x-axis. So limits at infinity, x is approaching positive or negative infinity instead of approaching like an x value. Usually we see x approaches c. Okay, so let's take a look at this. For the problem that we've got, f of x equals 3x over x squared plus 1, and we've got this lovely drawing for us. It's a little bit hard to see on your printouts, but here's what it looks like. It's almost like a teapot and then another teapot, except it kind of curves to get a little, I don't know, tiny little parabola bit there in the center. Okay, so let's take a look at the left side. We are getting really, really close to what number as x is going very far left? Okay, the y value is getting really, really close to 3. Okay, what if we get really far to the right? That's where x is going towards positive infinity. We are again getting really, really close to positive 3. Okay, so the limit as x approaches, over here now, limit as x approaches negative infinity of f of x is 3. And on the right side, the limit as x approaches positive infinity of f of x is also 3. These do not always have to be the same. Okay, you might have something that looks more like this. So you approach, I don't know, positive 3 over here and negative 3 over here for just a different problem. So finding the limit of a function at negative or positive infinity finds the end behavior of a function. You've talked about this back in like algebra 1 or 2, somewhere back there. Okay, there's a theorem for limits at infinity, and here it is. If r is a positive rational number, okay, rational means you can make a ratio or a fraction out of it, and positive is literally positive, non-negative. Okay, so that's going to be your exponent here. Okay, so it's got to be like a whole number or a fraction for your exponent. Okay, and c is any real number. So c on top is some kind of a real number. So it's just not an imaginary number. So it can be a whole number, it can be a fraction, whatever. Then the limit as x approaches infinity equals 0 if it's like c over x to the r power. Okay. If the numerator has a bigger exponent than the denominator, then you either go towards positive or negative infinity because the numerator gets super, super, super gigantic. Let's say that the denominator is bigger. Then the top stays fairly consistent, but the denominator gets gigantic. So a number divided by a giant number is going to be close to 0. So that's what the limit is going to be. And that's what we can see over here is that c is just a number and you divide it by something super gigantic. If you plugged in infinity here for x, you would get something super giant in that denominator. And then the last thing, if they have the same power, then your limit is the ratio of the leading coefficients. And that's what's known as a horizontal asymptote. So instead of vertical, it's a horizontal asymptote that your graph gets really close to on the edges. So you've definitely dealt with those before. It's just the first time this year so far. All right, let's look at the first example. We have x going towards positive infinity. So we're going to do a really weird looking thing. We're going to take whatever your biggest exponent is in the denominator, and we are going to divide every single term by that x. So we've got a power of 1 in the denominator. That's our biggest exponent. So we are going to divide every single little term by x. Okay, it's kind of like multiplying the top and bottom of the fraction by 1 over x, and then just doing it to each little individual piece. So this limit equals the limit as x approaches 0, x approaches infinity, of 2 minus 1 over x over 1 plus 1 over x. All right, so I have reduced the fractions 2x over x to just be 2. X over x reduces to 1. And then everything else that does not reduce, you just rewrite it. Okay, next we are going to, I'm going to air quotes this, plug in infinity. So if our denominator for this guy is infinity, 1 divided by infinity is 0. So that bit is 0. Down on the denominator, we have another 1 over x. 1 over infinity is also 0. So this is going to be 2 minus 0 over 1 plus 0. That reduces to 2 over 1, which is 2. B. The biggest exponent in the denominator is a 2. So we're going to divide every single term, top and bottom, by x squared. So this limit equals limit as x approaches infinity of 3x over x squared plus 5 over x squared over 4x squared over x squared plus 1 over x squared. So every little term, top and bottom, gets an x squared on it. All right, this equals the limit as x approaches infinity of, all right, 3x over x squared is the same thing as 3 over x, plus 5 over x squared is just 5 over x squared. That doesn't simplify. Bottom, 4x squared over x squared is 4, plus 1 over x squared is just 1 over x squared. What's going to become 0? Anything that still has an x on the bottom becomes 0 because you're trying to plug in infinity. So it's 3 divided by like 10 bajillion. That's got to be 0. So this is 0 plus 0 over 4 plus 0. 0 over 4 is 0. Last one in this row. We've got limit as x goes to negative infinity. So we do have to be careful when we're going towards negative infinity to see what happens. Think about plugging in super giant negative numbers. All right, we're going to divide everything by the biggest exponent that is in the denominator, which is a 2. So we've got limit as x approaches negative infinity of 5x to the 4th over x squared minus 2x squared over x squared over 4x squared over x squared plus 1 over x squared. What this really does is it makes the denominator become really simple, and then the numerator is as simple as it can get. All right, so this equals the limit as x goes to negative infinity of, reduce your fractions. Our first little fraction up here is going to become 5x squared minus second fraction, x squareds cancel, we're left with a 2. Denominator, x squareds cancel, left with a 4, plus 1 over x squared does not cancel, so we just keep it. I know these are not very pretty, however, they end up kind of beautiful. The x squared up here is going to be really gigantic. The x squared down here will be gigantic, but it's 1 over a gigantic thing, which goes to 0. All right, divide by something gigantic, you get 0. All right, so this equals the limit. Oh, I'm sorry, we're not doing limit anymore, we're plugging in. So we get something super gigantic on top that has not canceled out. So we have like, I'm going to do some side work. We've got 5 times negative infinity squared minus 2 over 4 plus 0. Okay, the denominator is just 4. The top, we are squaring negative infinity. Negative infinity times negative infinity is positive infinity. So this is 5 times positive infinity. Okay, anything times any positive number times a positive number is going to be positive. So this limit is positive infinity. Okay. Subtracting 2 and dividing infinity by 4, that's not going to do anything real. So we are done with that guy. Let's talk about some limits with trig functions, and it's going to be as x goes to infinity. Okay, let's take a look at the graph of sine of x. Sine of x starts at 0, 0. Well, it still exists to the left, but we do have a point there, and then it looks like this, and comes down, and then back to the center, and then up, and then back to the center, and so on. So as x goes to infinity, means goes as far right as you possibly can, and just keeps on going, right, right, right. What is the y value getting close to? Well, the y value doesn't really get close to one specific number because this graph continues in this up, down, oscillating motion. And since it keeps going back from like 1 to -1, all the way back up to 1, all the way down to -1, there is no y value that this function just like gets stuck on or stuck towards. So the limit as x approaches infinity of sine of x does not exist. So this is another case where a limit does not exist. It's where you have an oscillating function, oscillate, all the way to the right or to the left, and it doesn't converge to one spot. I'm going to say doesn't settle at one y value. Second one is the limit as x approaches infinity of sine of x over x. So this picture is going to look a little bit different. We've seen this one before. It looks like this. Okay. So this one is also an oscillating function. But the difference between just sine of x and sine of x over x is this function gets smaller. Okay. So we can use the squeeze theorem. We're not going to show like all of the steps of it, but the function 1 over x looks like this, like y equals 1 over x. And the function y equals -1 over x looks like this. So as we go further and further to the right, our purple function, the sine of x over x, is completely stuck in between the two red functions, 1 over x and -1 over x. Well, as x goes to infinity, this function goes to 0. So the limit of 1 over x is 0, right? As x gets really, really, really big, 1 over x is going to become 0. And same thing over here. It's just the negative version, so we get really, really close to 0 as we go this way. Okay, closer and closer and closer and closer. And then the purple function is just completely stuck in between. So it starts getting like even smaller on its oscillations. Like Notability is trying to make me get even like smaller and closer to a straight line. It's not letting me do something big. So using that squeeze theorem, our function that we actually care about, which is the sine of x over x, gets stuck in between two functions that get really close to 0, which means that this limit as sine of x, limit as x goes to infinity of sine of x over x is also going to equal 0. So we use the squeeze theorem, THM for theorem. And we can literally see how our function is getting squeezed between two other functions. The last couple of things that we are going to do with limits here has to do with e to the x and the natural log of x. Remember that these two functions, f of x equals e to the x and g of x equals natural log of x, those guys are inverse functions of each other. So when we draw them, they should look really, really similar. They should just look like a mirror reflection of one another across the line y equals x, so like a 45-degree angle reflection. Let's take a look at f of 0 and f of 1, so over here on the left, and that's going to help us draw e to the x. So first off, f of 0 means we are plugging in 0 for x, so that's e to the 0. And anything to the 0 power is just 1. So this is the point 0, 1 that e to the x goes through. Then f of 1 means e to the first power. E is not a variable. E is a constant. So this is just e, and e is really, it's a number that goes on forever, just like pi does. So it's 2.718-ish. Okay, so that's going to be 1, 2.718. Okay. This is an exponential function. So it's going to go through 0, 1 here. It's going to start out really, really close to 0 there, and then it just shoots up. All right. So let's do some limits of this function. We're going to do the limit as x approaches infinity, which is towards the right, of f of x. So as x goes towards positive infinity, we are going towards the right. Is there any limit on f of x? Well, this is a little bit like e to the infinity power. That is a super duper gigantic number. That is never going to level out and get smaller. Okay, e to the infinity doesn't actually make sense. It's just like e to the a billion, e to the 10 billion. So this gets really, really high, really, really quick. So that limit is infinity. You could say that the limit does not exist. So that's this one. Switch over to blue. Now we're going to go towards the left to negative infinity. That is this way. Exponential functions, if you follow the tail end, like the end that gets really low, it never actually touches 0. It's got a horizontal asymptote at y equals 0. So that means that our limit as x approaches negative infinity of f of x equals 0. All right, this way, natural log of x, g of 0 means natural log of 0. Can you take the log of 0? And the answer to that is no. It's because the way that logs work, logs mean like this is the same thing as log base e of 0 equals some number. And if you rewrite that in exponential form, that's the same thing as e to the number equals 0. Well, you can never take a number like e, remember that's an actual number, to another number and have it equal 0. So this does not make sense. So this does not make sense, which means that g of 0 is undefined. It's not a hole in the graph. It is going to be a vertical asymptote at x equals 0. I'm going to draw in that vertical asymptote with, how about green? Vertical asymptote. Beautiful. Okay, g of 1 means the natural log of 1, which is the same thing as log base e of 1. Going back to exponential form, that means e to the number of some sort, we don't know what it is, equals 1. Didn't we just talk about that? E to what power equals 1? Well, anything to the 0 power equals 1. That means g of 1 is 0. So we are going to go through the point 1, 0. We have a vertical asymptote. It starts down below, and then it goes this way. Do we see how hopefully that these two graphs are very, very similar to each other? It looks like that. Okay, mirror reflections. This is natural log of x. This is e to the x. All right, so let's take a look. Limit as x approaches infinity of g of x. That means as we go towards the right-hand side, it's going to be over here. Now, does that ever actually like level off? And the answer to that is no. Just like over here with the red, that one never really levels off either. Okay, we never have a horizontal asymptote, so it's not a horizontal asymptote there as x goes towards positive infinity. Okay, so since there's no leveling off and we just keep going forever, that means we are going to positive infinity very slowly. Okay, but we are going towards positive infinity. The other one that we've got here is as x approaches 0, and then there's a plus. The plus means from the right-hand side, so numbers that are just barely larger or to the right of 0. So that's going to be this way, right, from the right of x equals 0. So the limit as x approaches 0 from the right of g of x, well, that just moves down, 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 down forever. There's no like cap on that. So that limit as x approaches 0 from the right does not exist, but you could say negative infinity because it moves down literally forever.